Okay, so we can go back. We call this is a new idea, integrated motor drive. What is integrated motor drive? Means the driver and the motor become one set, like this. So you can see this is motor. Where is driver? Here. This is driver's house. How can you make a driver so small? Because you only use silicon carbide. Silicon carbide is very small, and you do not use capacitor, huge capacitor. So the capacitor is very tall and very large. Then you can put the circuit in this house. Then you can have integrated motor drive. So you have power electronics and the motor at the same location. So the idea is very good. If you can put this motor drive, then you can have an elevator. The elevator do not need a machine room. Otherwise you need a room to put motor and the inverter. But now you can put a motor and the inverter in the, this is an elevator in the wall. So you can save a lot of space. So this is the idea. So DC link capacitor occupy 40% of the volume of an inverter. So occupy 40%. If you need a capacitor, then you need a big inverter. Then you put here. Integrated drive about 7.5 kilowatt. So the maximum is 7.5 kilowatt. If you are more than 7.5 kilowatt, then the house is not enough. So it is only for middle and the low power motor drive. So above 7 kilowatt, the integrated drive become motors with large inverter. So you need a large inverter. Then the inverter cannot go here. Matrix converter will give same functionality as front-end drive system. Sometimes we call it is back-to-back inverter. Sometimes we call it is front-end. So which will mean input is AC switch. So input is AC switch. And we have capacitor. Then we have inverter. So we call this is back-to-back or front-end. So this is motor. So we call this is back-to-back. Or we call this is front-end. Active front-end. So in this case, it is very similar. So the matrix converter will provide the same function as back-to-back inverter. However, back-to-back inverter need a huge capacitor. Matrix converter, no huge capacitor. And we can do regeneration. So energy can go back from motor to grid. So regeneration. And the input current waveform is sinusoidal. And the input power factor is 1.0. But no large capacitor, no large inductor. The filter is a small capacitor and a small inductor. So it is okay to put in the house. So this is the advantage of matrix converter, small size and compact. So how can we design this? So we can see we have to use IGBT, bidirectional switch. But now we have module. So two IGBT into one module. So small module. So power electronics house in the motor and brake. So you have motor. This is your motor. and we put a house here, and we put power electrons here, attached to motor. So you can see the power electronics house here, in the motor end plane here, motor end. We have IGBT, we have diode, and we have filter capacitors. And we redesign this end house with extra fins, so we can get heat outside to cool the device. So we have to special design this one to get cooling. Special package device like Tenex semiconductor UK. They can have a module for 6 AC switch, 200 ampere bidirectional switch module to feed in the motor and the plane. So only one module, and everything is fine. So input power quality to match traditional back-to-back product. So the same function as back-to-back product, but we do not need a huge capacitor. So you can see this is bidirectional switch module, like this. And this is redesigned motor and plane. So you can easily get heat outside. So the circuit is here, and we can easily get cooling. So this is real product that people has made. So integrated motor drive. How about the other application? 100 kilowatt, so very huge. Matrix converter, 600 ampere, 1200 volt IGBT matrix converter. This is Arizona, USA. So 129 kilowatt and 150 kVA. The year is 2003. So this is a prototype of the matrix converter. So what is this? This is our device. What is this? We call this is bus bar. What is bus bar? Before, from here to here, you use a line. But a line creates straight inductance. So now you cannot use a line. You have to use a couple bar. So very thin couple bar. Maybe you put it like this, very thin. So you can see this is bus bar. No inductance, small resistance. So then you can have a very good layout. No spike, so no snapper. So this is the only way to do the layout. So you have to be careful about the layout. And how about your circuit here? 100 kilowatt matrix converter. You have DSP, you have FPGA, and you have clamp capacitor, and you have the main circuit, the bidirectional IGBT, something like this. And you can see this is bus bar. This is bus bar. So we have to do layout, otherwise the power is too huge. You cannot handle the huge power. So how many ampere? 400 ampere. So you can see this is the real output current. A phase, B phase, and C phase. The phase shift is 120. You can see it is quite close to sinusoid. So if you compare the matrix converter and the inverter, can you see the difference? No difference, right? For the output current. How about output voltage? You can see the difference. If you use an inverter, this is very smooth, one line, right? DC bus. But if you use matrix converter, the voltage is like this. So what is this point? Maybe 0.5, right? 0.5. So the voltage is like this. the minus voltage is like this: A phase, B phase, C phase, and the switching frequency it could be 1 kilohertz like this. So output current is huge, almost 400 ampere, so high power. How about the control board? So this is a control board. We use a microcontroller, FPGA, and a DSP. And we use fiber optical link to get driver. So you need a fiber optical link to get driver to avoid the EMI. And the analog input board, so ADC, A to D converter. And you have FPGA, you have microcontroller. So this is the universal control board for 100 kilowatt. And this is manufactured from university. So I think it is a PhD student dissertation. So this is matrix converter, but we use another device, MOS control thyristor. And this MOS control thyristor disappeared. Originally, it used MOS to control thyristor, but the performance is not good. So now it is disappeared from the market. So you can see this is bus bar. And we have current plug here. We have clamp, so capacitor clamp. We have input, and we have a lot of circuit. This is matrix converter. 3-phase input, 3-phase output. So this is a real product for MOS control thyristor matrix converter. This is dynamo motor. So we have induction motor here. This is the load. So we use the load coupled to the induction motor to provide the external load. So this is matrix converter test rig. So this is dynamo motor. So how can you control this motor? So we call this is field orientation control or vector control. So we have speed command here, we have feedback speed here, then we have speed error. We design speed controller to provide Q-axis current. And we do the flux weakly to provide D-axis current. Then we design D-axis and the Q-axis current regulator. And then we compensate the back EMF, and then we can provide the DQ voltage and a converter to ABC voltage and provide to matrix converter. And we have input voltage 60 Hertz, and we have matrix converter here. Then we use the matrix converter to drive a motor. So we have to detect the current of the motor, and then we convert ABC current into DQ current. So this is the block diagram of the matrix converter control algorithm. So this is a real implementation. So what is the result? So 20 ampere, so A phase, B phase, C phase, 1 kilohertz. And how about output voltage? You can see this is because we do not provide any DC capacitor, so the voltage is changing. This is minus sign, so A phase, B phase, C phase. Although the voltage is not close to sinusoidal, but the current is very close to sinusoidal. So you can see the matrix converter still provide a very good performance. So the output frequency 40 Hertz, input frequency 60 Hertz, switching frequency 4 kHz, 12 horsepower. So this is the current when speed is reverse. So here speed is 0, then the current reverse. So you can see this is symmetric. So speed reverse from 300 RPM. This is 300 RPM. This is minus 300 RPM. So they are symmetric. And the switching frequency 4 kHz. Input frequency 6 Hz. 12 horsepower induction motor load. How about the current? Almost 20 ampere. 20 ampere. So you can see this is the speed reverse result. So this is matrix converter, 3 kilowatt, 3 kilowatt. And it is used for airplane, electro-hydraulic actuator for airplane. 3 kilowatt. So how large is it? This is, you drink coffee. This is coffee cup, right? So how many coffee cup? Maybe 3 coffee cup. So for how many kilowatt? 3 kilowatt. So this is for electro-hydrostatic actuator. So it is used for an Airbus airplane A320 airline. So this is a real product we can apply for airplane. So small size and high power density and very reliable and compact. How about the current? So 7 ampere. So this is sinusoid, A phase, B phase, C phase. So input here. So for airplane, what is the airplane frequency? 360 Hz, not 60 Hz. So for airplane, the normal frequency is 360 Hz. So I want to ask you one question. Why? Why not 60 Hz? In ground, we usually use 60 Hz. But in airplane, why do you use 360 Hz? Why? Anybody has any idea? The reason is you have inductor. If your frequency is higher, your frequency is 360 Hz, 6 times, then the same reactance, but your inductor becomes 1/6 smaller. Your motor becomes smaller. The reason is your frequency is higher, but your reactance is the same. So your inductor becomes smaller. If you have a small motor, then your size becomes smaller. So this is the reason airplane like to use 360 Hz to make everything become smaller. So you can see the input is 360 Hz and the output is 42 Hz. So this is the experimental results. So this is the test bench. So we have the motor here and use the matrix converter to drive the motor. We put the dynamo moment and to test. So this is the EHA actuator for airplane to test in the load. This is a real result. I believe this also a project come from university. So this is a speed change from 10,000 to minus 10,000. And this is the current, and this is the current, A phase current, B phase current, C phase current. So when speed reach 0, this is a symmetrical point. This one and this one are symmetrical. So this is a 0 speed. So you can easily check everything. So the current is 10 ampere, almost 10 ampere. But the speed is very high, 10,000 RPM. So this is a test. If we have external load, then you can say see the speed drop, but can recover quickly. And this is Q-axis current, and this is input current. This is experimental results. This is a pollution control. So we use the actuator to control pollution. From this pollution, then we move to this pollution, then we have track this command. So this is response. So they have delay, but then finally they can track. This is the speed. This is pollution. This is speed. This is Q-axis current near 10 ampere. So this is measurement results for pollution control. And this is the load, the motor demonstration, the real motor. So then we can have a brief conclusion. So the matrix converter, what is the advantage of matrix converter? First, bidirectional power flow, unity power factor, sinusoidal input current, sinusoidal input voltage. So small size, we can do regenerative operating, which means sometimes the motor gets power from wind. Sometimes the motor can provide power to wind. What is the purpose? Saving energy. Before, if you need to reduce your speed, you use a resistance to waste your power. But now, you can return power to power grid. Then you can save energy. So regenerative operating. And then you have sinusoidal input current, sinusoidal output current. You have unity power factor. You have one stage power conversion. You have high efficiency. So you get some advantages. But what is your disadvantage? Your DC bus only 6.6%. So this is your disadvantage. And the modulation control is not easy. I think it is not easy. You need a lot of computation. And we can use new power device like silicon carbide. Then we can make the matrix converter become more attractive. So the current issue of matrix converter is not theoretical, it is application. So we still found some institute they focus on matrix converter, especially in UK. So they have PhD students, maybe every issue they will publish their application for matrix converter. And we also receive some special issue for matrix converter. So matrix converter is a new trend to do AC to AC converter. So it is better than traditional rectifier and inverter, because traditional rectifier and inverter need a huge capacitor. And the input current is not good. It is discontinuous. So if you check the input voltage is here, but how about your input current? It is like this. So this is 200 ampere. So you can reach peak value and drop to zero quickly. Then it creates EMI. It creates disturbance. So this is not good. If you want to improve this, what can you do? You have to design PFC. How can you design PFC? Front end active filter. But it costs a lot. So now we think of why don't we just design AC to AC? So this is AC to AC converter. So it provides some advantage, but it also provides some disadvantage. So we call
this is engineer. What is engineer? A trade-off. So nothing is perfect. If one thing is perfect, the other thing should be disappear. But now, the world still have inverter, still have matrix converter, because they provide advantage and also provide disadvantage. So if you are interested in this field, I think it is very interesting and very attractive. And in the world, a lot of people still work in this field. So I think that this is the end of matrix converter. Okay. So now we will move to DC to DC converter.
DC DC. We finish AC to DC. We call it is rectifier. It is a phase converter. We also discuss about DC to AC. We call it is inverter. We also focus on AC to AC. We call it is cycle converter and the matrix converter. Now we will move to DC DC converter. So what is DC to DC converter? If you have a cell phone, what can you do?
So you have AC 110 volt. Can you use the AC 110 volt direct to your cell phone? No, you will damage your cell phone. So what should you do? You have to do rectifier. But before you do rectifier, maybe you need a transformer to reduce your voltage. So use a transformer to change 110 volt into 6 volt. Then we use rectifier. And then we use capacitor. And then we can use the voltage to charge our cell phone. So this is our law.
So traditional we use this way. We reduce our AC voltage. We use rectifier, and then we use small capacitor, and then we use low. But the problem is this, because the frequency is 60 Hertz. If the frequency is 60 Hertz, then you need a transformer. And here is 110 volt. So you need a lot of turns, a huge transformer. If you need a huge transformer every day, what do you need to bring? You have to bring your cell phone, and you have to bring another charger, right? Because it is so huge. So you need a huge charger. So size is huge because transformer. Do you like to do this? No, you say I don't like to do this. So I need a small charger. If you need a small charger, can you use 60 Hertz? No, you have to increase your frequency, right? Then you can reduce your size. So we have to change the topology. So now people use new idea to design DC to DC converter. What is the purpose? Small size. Small size. So we need a small size. So if you work in electronics lab, so you can get a power supply. So you see, oh, this is my power supply. So what is the voltage? 30 volt, right? And what is the current? Maybe 1 ampere. And how huge is very huge? And you can see we have a fan at the back to cooling. So you can see how many watt? 30 watt. Too huge.
So now, if you have a DC-DC converter, 30 watt, you can put it in my pocket. Become very, very small. Maybe only 1% of original. So you can see DC to DC converter is very successful. We can design small size. We can design low cost. And we can design reliability and cheap product. So it is very successful. It is not like inverter. If we discuss about an inverter, we say, what do we use? We use rectifier. We use huge capacitor. We use inverter. Then, how about your power factor? 0.6. How about your current harmonics? Maybe 60%. Do you think that this is good? Not good. Why don't you change? No one wants to change because we cannot design a very cheap and a very reliable inverter. You can design matrix converter, but it is not cheap. If you cast a law to say we have to improve the power quality, then everybody have to design matrix converter. Then the price become 1.5. Do you like to do this? Nobody wants to do this. So we still accept it. But for DC to DC, we are very successful. If you want to sell your charger to Europe, they say, oh, you have to certify our rule. Our rule include power factor correction. Our rule include harmonics. If you do not pass the regulation, you cannot sell because everybody can do that. So it is different from inverter. It is very successful. Why? Because people put a lot of efforts for DC to DC converter. So we will discuss this issue. And recently there is a new idea we call soft switching. If you use soft switching, then you can reduce your switching loss. If you can reduce your switching loss, then you can improve your efficiency. If you can improve your efficiency, then your loss become very small. Then you do not need any fan. So you become small size. So we will discuss about the development of DC-DC converter. So how many types do you have for DC-DC converter? If you consider electricity, so how many types do you have for electricity? So if you study electricity, how many types? Only 2 types, DC and AC, right? DC and AC. Which one is better? DC is better or AC is better? If you think DC is better, please raise your hand. If you think AC is better, please raise your hand. Which one is better? When people develop electricity, there are 2 companies. One is Edison, another is Westinghouse. They fight each other. And I think Edison support AC, but Westinghouse support DC. But finally, who win? AC win. Why? Because your electricity, you have power plant, but you have a long distance. So you have to have transmission. Then you need to increase your voltage. And when the electricity arrives city, you have to reduce your voltage. What kind of machine can you use? Transformer, right? So you can use transformer. Transformer is very simple, just different terms. If you use DC, do you have transformer? No. What can you use? You only have buck boost. But buck boost is simple or difficult. Very complicated. So for 100 kilovolt, can you use a buck converter? Very hard. So people found that AC is easy to handle because AC has transformer. DC is more challenging because DC has no transformer. So originally people believe AC is better than DC, right? AC is better than DC. So we need a centralized power plant, and we can transfer transmission for a long distance by using transformer. But now people change the idea. They say AC is not good because power plant is too huge. It is too dangerous. So what do we need? We need microgrid. What is microgrid? Solar cell, right? And we call solar cell. And we have wind generator. So we have different power. But do you think microgrid is DC or AC? Solar cell is DC or AC? DC. So now people say AC is not good, DC is good. But before, people say AC is better than DC. 200 years ago. But now people say DC is better than AC. Why? Do you know why? Because we have some problem about the environmental problem, right? Because CO2 problem. So people need a renewable energy. But the renewable energy comes from DC, not from AC. And it couldn't be too huge. So they say microgrid, only this city use it. So you don't need to transport to a long distance because everywhere is your power plant. So now people change idea. So you can see for electricity, the idea is very simple, either DC or AC. And people fight each other and argue about this issue. But finally people choose AC. But after 200 years, people change idea. They say DC is better than AC. So currently, because we use DC, so power electronics become more and more important. So we need energy conversion. So we need power electronics. So if you check the renewable energy, everywhere use power electronics. So can you design a huge storage energy? Can you design a huge battery charger? Can you design a huge microgrid? So it becomes challenging, right? And you need a lot of power electronics technology to support you. Otherwise, you cannot develop renewable energy. So we think power electronics become more and more important, such as electrical vehicle. What is electrical vehicle? You use battery. Do you think the battery is AC or DC? DC, right? And then you use battery, you design inverter, and then you drive motor. You change DC to AC. So how can you make the battery can be drive for a long distance? This is one issue. How can you design fast charge of battery? Another issue. So every issue related to what? Power electronics. So you can see power electronics become more and more important because everything need conversion. DC to AC, AC to DC. So people change idea. Before we think AC is God, everything should be AC. But now people think AC is not God, DC is God, right? So they change idea. So we will discuss about the DC to DC converter. So I will see you next week.